You know that sound, right? That iconic clicking? It's the sound of the invisible world of radiation being made real. But have you ever wondered how it actually works? How does a simple metal tube take these tiny, unseen particles and turn them into a sound we can actually hear? Well, today, we're going to pull back the curtain on the incredible physics of the Geiger counter and see how this elegant chain reaction makes the invisible audible.
So here's the big question, really a fundamental challenge in physics. How in the world do you even begin to measure something you can't see, touch, or feel? We're talking about single alpha or beta particles, things that are ridiculously small and moving at insane speeds. The Geiger-Muller counter is just a brilliant and honestly a surprisingly simple answer to that very big problem.
So here's our game plan. We're going to follow a single particle on its journey. We'll trace its path from the exact moment it zips into the detector, see the wild chain reaction it sets off, and follow it all the way to the final step that gives us that famous click. Okay, before we get to the action, the cascade of events that makes this whole thing work, we need to set the stage. We've got to understand the very carefully controlled environment inside that Geiger-Muller tube. This is where all the physics happens. You know, the beauty of the Geiger-Muller tube is how simple it really is. At its heart, you've got a hollow metal tube, that's our cathode, and a super thin wire running down the middle, that's our anode. But the real key, the secret sauce, is what's inside, a special gas, usually about 90% argon and 10% something like ethanol. The argon is what we're trying to detect with, and that ethanol, well, it plays a really important job later on in resetting the whole system. Now, we crank up the power. We're talking a few thousand volts between that central wire and the outer tube. This creates a powerful electric field. And because of the shape, a thin wire inside a big tube, that field gets incredibly strong, like super intense, right near the surface of that central wire. This little high field region is the action zone, where our tiny particle signal is about to get a massive boost.
All right, our stage is set, the electric field is humming. Now, let's bring in our star player, a single particle from a radioactive source. It could be an alpha, a beta, maybe a gamma ray, and it's heading right for our tube.
So, as this particle zips through the argon gas, it's like a bowling ball through pins. It transfers some of its energy to the gas atoms it bumps into. If it hits an atom hard enough, it can actually knock an electron right out of its orbit. This is called ionization. And what we're left with is an ion pair, one free electron and the now positively charged argon atom it left behind. This tiny little event is the seed, the spark that's going to start the whole fire.
But here's the thing. One little ion pair, that's a tiny, tiny electrical event, way too small to detect on its own. The real genius of the Geiger counter is how it amplifies this one little event by a factor of, well, billions. This is where the magic really happens, in something called an electron avalanche. It's a perfect example of a controlled chain reaction. So, remember that crazy strong electric field near the center wire? Well, that first free electron gets yanked towards it, accelerating to an incredible speed. It picks up so much energy that when it inevitably slams into another argon atom, it ionizes that one too, knocking another electron free. Now you have two, and they both accelerate, and they both hit more atoms. You see where this is going? It's a cascade, an avalanche.
This is the perfect way to think about it. That one initial electron triggers an exponentially growing chain reaction. What started as one single, quiet event has, in just a few microseconds, turned into this massive, dense cloud of electrons and positive ions. A huge commotion from a single push.
It all starts with just one single electron, knocked loose.
But that's just the start. The avalanche multiplies it into a pulse with not just millions, but potentially billions of electrons. And that is a huge electrical signal that our electronics can easily pick up. This incredible amplification is what makes the Geiger counter so darn sensitive.
Okay, so we've created this massive swarm of electrons, we've got our signal, but how do we turn that into a number on a screen and, of course, that famous click?
It's actually pretty straightforward from here. The entire cloud of electrons slams into that central wire pretty much all at once. Bam! That creates a sharp, clean little pulse of electricity. That pulse gets sent out to some circuits that clean it up, make sure it's a real signal and not just some random noise, and then it tells the counter to tick up by one, and of course, it triggers the speaker to make that satisfying click. Now, this system is amazing. It's incredibly sensitive, but it's not perfect. It has one really important Achilles heel, something we in the business call dead time.
Think of it like this. Right after that huge avalanche, the tube is kind of messy. There's this cloud of the leftover positive argon ions, and they're big and slow. They hang around the central wire for a moment, and they temporarily shield the electric field. Until that cloud clears out of the way, the detector is totally blind. It can't start a new avalanche. So for a brief moment, it's completely insensitive to any new particles coming in.
So how long is it blind for? About 200 microseconds. Now that sounds incredibly short, right? And at low levels of radiation, it is. It's no big deal. But if you're in a high radiation field where particles are hitting the detector constantly, you can actually start missing them because they're arriving while the detector is still rebooting. And that can cause you to seriously underestimate how much radiation is actually there. And this really gets to a fundamental trade-off in designing particle detectors. You're always balancing sensitivity against speed. For the really high-octane experiments, like at particle accelerators where things are happening incredibly fast, you need different kinds of detectors that have much shorter dead times. It really highlights this constant push in physics, this quest to build faster, more efficient eyes, so we don't miss a single fleeting moment in the subatomic world.